Thank you. Hi, I'm Pritom. I'm a grad student at UC Davis. I work with Chris Fasnath and TD Cosmo collaboration. This project involves several people, including me, and led by Anwar Shojib, who is a Anston Fellow and a postdoc at U Chicago. And the title of my talk is Improved Hubble Constant Measurement using a specially resolved Pelletier dispersion. So Hubble constant is the current expansion rate of our universe. There are several methods to measure the Hubble constant. These methods could be divided into two groups. One group uses early universe data, such as temperature and polarization fluctuations in cosmic microwave background radiation. Another group uses local universe data, such as type 1 supernova. And there are 5 sigma difference between the measurements of these two groups, which is called Hubble tension. Sorry. Okay. Yeah. And in the top part of this plot, I have grouped together all the early universe probes, and in the lower part, I have grouped together all the local universe probes. And you can see the median value of the early universe probes is around 67, 68, and the median value of the low universe probes is around 72, 73. So one independent measurement method from the local universe side is strong lensing time delay method. And in the purple ellipse, you can see all the Hubble constant measurement from this method. So how do we use a strong lensing method to measure Hubble constant? To apply this method, we need a strong lens system where there is a deflector, such as a massive galaxy in the foreground, and a time-varying source, such as a quasar or supernova in the background. So when the light from the source passes in the proximity of the deflector, gets lensed, and we get several images of the source. So here is the lens system we used in this work, which is called RxJ1131. And this is a high-resolution image taken by Keck system, and you can see the lensed galaxy in the middle, and then the images of the quasar here, also the arcs of the host galaxy. So when the photons from the source emits, and they emit at the same time, however, they reach at different images with relative delays. We can observe or measure these delays by looking at the light curves from the images of the source. In here you can see the light curves from the 4 images of this lens system observed by 1 meter class telescope. And we can combine this time delay data with gravitational potential information, which we can model using high resolution image. And from there, we can get combination of cosmological distances. And from cosmological distances, we can infer Hubble constant. However, there is a major challenge when we apply this method. And this is called mass sheet degeneracy. So what happens when we are modeling the gravitational potential, we need to assume a mass model. So let's assume a power law model. And if we draw the power law model in log-log space where y-axis is the density and x-axis is the radius, it's a straight line with a slope, right? And it fits the lensing data well. Now we can scale this power law model and add a constant mass sheet with it. And we get another mass model, which is not a power law model. However, it fits the lensing data well. So that's the degeneracy. Like from the lensing data alone, we cannot say which mass model is correct. However, these two different models predicts two different H0 value. So if we don't know which mass model is correct, we don't know which H0 value is correct. We can break this degeneracy using 2 ways. One is we can assume a mass model and implicitly break this mass sheet degeneracy. However, if we do that, if the mass model is not correct, we don't know whether H0 is correct or not, right? Another way to break this degeneracy is to use stellar kinematics, because stellar kinematics is sensitive to mass. And if we do that, we can use a flexible mass profile, which will not bias H0 measurement. So we did that. We used 7 lens system, and we used lensing data and time delay data and analyzed all of them together with a power law mass model. And using those data, we got a 2% estimate of the Hubble constant. So here the black curve is the probability density of the Hubble constant using those 7 lens system and power law model. And this blue curve is the Hubble constant measurement only from the single lens, which is the lens we have used in this work, with a power law model. To compare, this orange strip is the measurement from the early universe probe from the CMB data, Planck, and this is around 67, and this is the Schu's collaboration, which uses type 1 supernova data, and which is around 72. So you can see our probe is like local universe probe, so sits well with the local universe probe, and uncertainty is small, but we are not sure whether we got the correct thing or not because we have used a power law model. So that's why we used a flexible mass model. We used the same 7 lens system with the data before, but we analyzed them with a flexible mass model, and we break the mass sheet degeneracy using single aperture velocity dispersion. And doing that, we get this estimate of the Hubble constant, which is a 8%, 9% estimate. You can see the median value is almost same as before. However, the uncertainty goes up because we are using a flexible model, and single aperture velocity dispersion cannot catch everything. So there is another degeneracy which could not be broken using single aperture velocity dispersion. And that's mass anisotropy degeneracy. So what happens? We could have different mass giving us same single aperture velocity dispersion. So how is that happens? So we can have a bigger enclosed mass, and the velocity dispersion tensor is less aligned with the line of sight. In another scenario, we can have a smaller enclosed mass, but the velocity dispersion tensor is more aligned with the line of sight. So this could give us the same single aperture velocity dispersion. So we don't know which one is correct, right? However, especially resolved velocity dispersion can help us break this degeneracy. So especially the velocity dispersion helps break us this mass anisotropy degeneracy and also mass sheet degeneracy. That's why we are collecting especially resolved velocity dispersion. We observed this RxJ11 lens system using KCWI. Here is a white light image of the data cube, and you can see here the data from 2 different spectral, and you can see how the contribution from the lensing galaxy and the quasar is changing when the position of the spectral is changing. We only use data within this yellow contour. And again, this is the first time we are using especially resolved velocity dispersion data to measure Hubble constant. So we took the data, especially the velocity dispersion data from KCWI, and combined that with previous time delay data of this lens system and lens modeling data also from the previous system, and analyze those with maximally flexible mass model. With that, we got a 9% estimate of the Hubble constant. So here the red curve is that probability density of the Hubble constant. You can see, I'm just compare this red curve with the blue curve. You can, because both of them are from the same lens system, but the difference is that the blue curve is from power law, using a power law model, and this one is using a maximally flexible model, but with especially resolved velocity dispersion. So you can see the median is again same, but the uncertainty goes up. However, this is an improvement because if you compare the green curve and the red curve, you can see they have same level of precision. And this green curve we got from 7 lens system, and we got the same level of precision only from 1 lens system with a special resolve velocity dispersion. So that's an improvement. So to summarize, special resolve velocity dispersion helps us to constrain Hubble constant. For this work, we got an estimate of 9%. And this is an excellent agreement with previous TD Cosmo work, both with power law model and maximally flexible mass model. And now we have KCWI, KCRM. We can observe high redshift lenses. So this lens is the lensing galaxy from redshift 0.3, and the source is from redshift 0.7. So we can observe the other lenses which are at high redshift, and hopefully when we combine these data, we will get a higher precision level. Thank you.